The universe is dying around you. Not in some distant future measured in eons your mind can't quite grasp, but now, today. In the quiet span of time, it takes you to read these words. Stars are still being born, yes, but not like before. One by one, across the darkness, more are fading than rising. Galaxies are slowly running out of the cold hydrogen that could have become new suns. The great cosmic forge, the one that once lit up the universe with 10,000 newborn stars every second, has grown tired. Its output has thinned to a fraction of what it once was, and that fraction keeps shrinking. This isn't the beginning of the end, it's the middle of it. We like to imagine the universe's final breath as something unimaginably distant, trillions of years away, safely beyond concern. But the truth is quieter, more unsettling. The ending didn't wait for us. It started long before we arrived. The peak of creation is already behind us, 8 billion years behind us, to be precise. And this isn't a theory. It's something we've measured. Astronomers don't guess this story, they watch it unfold. They look out into the night and see galaxies so distant that their light has been traveling for billions of years just to reach us. What we're seeing isn't the universe as it is, but as it was. Every deep observation is a window into the past. Look far enough, 10 billion light-years away, and you're looking 10 billion years back in time. You're witnessing a younger universe, a more vibrant one. And when you line up those snapshots, something remarkable appears. A curve, a rise, and then a fall. A story with a beginning, a brilliant middle, and a slow, quiet decline, the very chapter we now inhabit. The universe didn't reach its creative peak in its chaotic infancy, not in the first billion years after the Big Bang. Back then, everything was too hot, too turbulent, too raw. It took time for things to settle, for hydrogen to cool, to gather into vast, silent clouds, for the first stars to live, die, and scatter the heavier elements needed to build something more. Only then, billions of years in, did the universe truly come alive. Somewhere around 5 to 6 billion years after the beginning, star formation reached its zenith. And then, almost imperceptibly at first, it began to fall. We missed it. Every moment of human history, every thought, every story, every memory has unfolded on the downslope. We didn't arrive at the height of creation. We arrived just after the music started to fade. If the universe were a party, we arrived late. Not just fashionably late, but after the peak. After the loud laughter and crowded rooms, after the music had already started to fade, and the guests, one by one, had begun to slip out the door. We live in the long afternoon of it all. The dimming hall, the moment when the lights are still on, but something essential, the energy that once filled the room, is quietly draining away. And unlike a party, there's no second wind coming. The universe doesn't loop. It doesn't refresh. There's no hidden reset waiting in the wings. Hydrogen burns. Stars exhaust themselves, and what's left behind cools, settles, drifts into forms that can no longer ignite. This isn't a story about some distant, unreachable future. It's a story about now. About where, exactly, we stand in the full sweep of everything that has ever happened, and everything that ever will. Because if the universe has a story, and it does, and if that story has a peak, then realizing we're already on the far side of it changes something fundamental. It shifts the weight of existence itself. It means we are latecomers to a process already winding down. It means the golden age of the cosmos isn't ahead of us, it's behind us. It means the night sky you look up at, dense and glittering as it seems, isn't a grand finale. It's a quiet afterimage, a sparse remnant of something once far more alive. Every photon of starlight reaching your eyes tonight is a whisper. a faint echo from a time when the universe didn't whisper at all. It roared. The question, then, isn't whether this is true. The evidence is overwhelming. The real question is harder, more personal. What does it mean to be alive in the aftermath? Cosmology, the study of everything, is also, in a strange way, the study of when. Not just where we are in space, which is already difficult enough to comprehend, but when we are in time. And that's a question most people never think to ask. We're very good at placing ourselves geographically. You know your city, your country, your place on the map. You know you're standing on the surface of a planet orbiting a star, tucked into the outer arm of a spiral galaxy. But when are you? Not the date on your calendar, not the year you were born, but your position in the entire lifespan of the cosmos, from its first breath to the last possible moment when anything can still happen. Because in a universe with a beginning and an ending, timing might be the most important thing of all. That lifespan is not infinite, or rather, it may stretch on forever in time, but not in event, not in meaning, not in possibility. There is a window, a fragile, fleeting stretch in which anything truly interesting can happen. A span where stars are born, where planets gather from dust, where chemistry grows restless and begins to organize itself into something more, where life emerges and, somewhere along the way, becomes aware enough to ask where it came from. That window didn't open immediately. It took time, about 100 million years after the Big Bang, for the universe to cool, for hydrogen to settle, for gravity to begin its quiet work of pulling matter together. And that same window will close. Not suddenly, not with violence, but with a kind of quiet resignation, a slow exhaustion of fuel, a gradual dimming, a universe that doesn't end in fire, but in the simple, inevitable act of running out. The best estimates suggest that star formation will continue for perhaps another trillion years. That sounds like forever. But the pace will keep slowing, inching downward, approaching zero like a fading heartbeat. The universe won't run out of time. It will run out of things to do with time. And if you could go back 8 billion years ago, you would find a universe that was far more alive than it is now. A universe doing more with every moment than it ever has since, or ever will again. We know this because we can see it, not directly, but by looking outward, deeper and deeper into space, we are also looking backward into time. Instruments like the Hubble Space Telescope and the James Webb Space Telescope peer across unimaginable distances, capturing light that began its journey when the universe was still young. Some of that light left its galaxies when the cosmos was less than 1 billion years old. By collecting thousands of these distant snapshots, measuring the glow of newborn stars within them, astronomers have been able to piece together something extraordinary. A timeline, a pattern, a curve. In the beginning, star formation was hesitant, sparse. The universe was still unsettled, turbulent from its own birth, filled with invisible scaffolding of dark matter that had only just begun to gather hydrogen into dense enough regions to ignite. But then, something changed. By 2 billion years, the pace was quickening. By 5 billion years, the universe was in full motion, almost frantic with creation. Stars were forming at rates 10, 20, even 30 times higher than what we see today, depending on the galaxy. It wasn't quiet. It wasn't fading. It was a universe at its peak, burning bright, building structure, filling the darkness with light faster than at any other time before or since. And we came after that. Then the peak passed. Not with a sudden drop, not with any dramatic signal you could point to, but quietly, almost imperceptibly, like a breath slowly leaving the room. By 8 billion years after the Big Bang, the universe had already begun its long descent. The great era of creation was no longer rising, it was receding. By the time our solar system formed, around 9 billion years after the beginning, the shift was already well underway. The cosmos had entered its twilight phase. Not dark, not empty, but undeniably quieter than before. And now, here we are, 4.5 billion years after that moment, roughly 13.5 billion years since it all began. We are not near the start. We are deep into the decline. Stars are still being born, yes, but the pace has slowed to something almost humble. The Milky Way, vast as it is, produces perhaps 1, maybe 2 new stars each year. At the peak, galaxies like ours were producing 10 or more. 10 times the light, 10 times the possibility, 10 times the raw creative energy. And now, a fraction. What's important is this: nothing external caused this. There was no switch flipped. No force that came in from the outside and dimmed the universe. This is something deeper, something built into the nature of reality itself. It is thermodynamic, structural, inevitable. The universe began with a vast endowment of hydrogen. Simple, pure, full of potential. And over time, that hydrogen has been steadily transformed, fused in stellar cores into helium, then into carbon, oxygen, iron, the building blocks of complexity. But in doing so, it changes permanently. Every atom that passes through a star comes out different and less useful for starting the process again. Those elements don't just vanish, they get locked away. In the cold husks of dead stars, in the silent pull of black holes, in planets that drift, frozen and inactive, places where creation no longer happens. Every star that dies takes a small piece of the universe's creative potential with it. And that loss is permanent. The hydrogen that fused into helium billions of years ago is still helium today. It will remain that way for trillions of years, stable, quiet, and unable to reignite the process that once made stars possible. Yes, there is some recycling. When massive stars explode as supernovae, they scatter material back into space, seeding new generations of stars and planets. But there's a limit. They can't reverse what's been done. They can't turn helium back into hydrogen, because the universe follows a rule that cannot be negotiated: entropy. The arrow of time points in one direction, and it never turns around. Toward equilibrium, toward balance, toward a state where nothing much happens anymore. A future where all the hydrogen has burned, all the stars have lived and died, and what remains is a vast, cooling expanse of quiet remnants, slowly radiating their last traces of energy into an ever-expanding void. And here's the part that changes how you see everything. We are not standing at the beginning of that process. We are already inside it, not at the edge, but somewhere in the middle, already past the halfway point. If star formation is the measure of a universe's vitality, the decline isn't coming. It's been unfolding the entire time we've been here. You are sitting in a universe that has already spent most of its best fuel. The sky above you is quieter than it once was. Darker, in ways that aren't immediately obvious. The vast spaces between galaxies have stretched wider. The great clusters that once blazed with the light of countless newborn stars are now dominated by age, by swollen red giants nearing their end, and faint white dwarfs quietly cooling into obscurity. And the future? It will be darker still. Not because the universe is collapsing, there's no dramatic implosion waiting for us, but because it is doing the opposite. It is expanding. And not just expanding, accelerating. Driven by something we barely understand, a force we've named dark energy, the universe is slowly pulling itself apart. Galaxies far beyond our local group are already slipping away. Given enough time, they will recede so far, so fast, that their light will never reach us again. They won't disappear because they've died, but because the space between us and them will be growing faster than light can cross it. They will fade, not into darkness, but into absence. This is the shape of the story. A rise, a peak, a fall, and then an eternity of silence. But why there? Why did the universe reach its peak 8 billion years ago, not earlier, when everything was denser, when gravity held more tightly? Not later, when more time had passed for matter to organize itself. Because that moment was a rare alignment, a collision of forces that created a kind of cosmic sweet spot, conditions that existed only briefly and will never return. In the early universe, things were too wild, too hot, too chaotic, too unstable. After the Big Bang, matter hadn't yet learned how to settle. Dark matter had begun pulling hydrogen into vast halos, yes, but those halos were constantly colliding, merging, tearing themselves apart. Any fragile cloud that tried to collapse into a star was often disrupted before it could finish the process. And then there were the first stars. Massive, short-lived, violent. When they died, they exploded as supernovae, blasting shockwaves through space, heating nearby gas, preventing it from cooling and condensing again. It was a universe that couldn't sit still long enough to create sustainably. It was unruly, like a child throwing energy in every direction, without structure, without patience. But time changes everything. After a few billion years, the chaos began to soften. The expansion of space cooled the universe just enough. Hydrogen could finally settle into stable clouds, cradled within those same dark matter halos that once disrupted them. The first true galaxies began to form, not the grand spirals we see today, but smaller, irregular clumps. Dwarf galaxies, quietly assembling themselves in the dark. And then they started to come together, merging, colliding, growing. Each merger funneled vast rivers of gas into the centers of galaxies, where it piled up, compressed, dense, ready, and ignited, in spectacular bursts of star formation. The universe, for a brief time, found its rhythm. It had what it needed: cold gas, abundant and untouched, gravity, strong enough to gather it, and just enough calm to let creation happen efficiently. The gas hadn't yet been depleted. It hadn't been overheated by generations of stars. It hadn't been blown away by the fierce winds of black holes. It was a perfect balance, a moment where everything aligned. And for that brief window, the universe burned brighter than it ever had before, or ever will again. This was the Golden Age. Not because it was peaceful, but because everything was finally working together. Galaxies were smaller then, but denser, alive with motion. They collided often, not as rare catastrophes but as a kind of cosmic rhythm. And with every collision came pressure, shock waves rippling through vast clouds of gas, compressing them, igniting them, giving birth to waves of new stars. It was messy, violent even. But it was productive. At the centers of those galaxies, supermassive black holes were already there. But they hadn't yet grown powerful enough to choke the very systems that fed them. Their radiation hadn't begun sweeping gas out into the void. The fuel was still abundant. The balance, delicate, temporary, was holding. The universe had reached a rare equilibrium, old enough to be structured, young enough to still be rich with possibility, and for a time, everything flourished. Then, quietly, the balance tipped. The black holes grew heavier, the supernovae multiplied. The very stars being born began to reshape their environment. Gas, once cold and cooperative, started to heat, to scatter, to drift beyond reach. The conditions that once encouraged creation began, slowly but inevitably, to resist it. Star formation became self-limiting. Every new star carried within it the seed of fewer stars to come. The universe was spending its inheritance, and there was no one, nothing, to replenish it. This is what we mean when we say the universe peaked 8 billion years ago. Not that it stopped, but that it crested, that the curve turned, that everything since has been a softer echo, a slower, quieter, dimmer version of what came before. And now, you're here. So ask yourself what that means. Not in the golden age, not in the furious, chaotic youth of the cosmos, but here, in the long descent. If intelligence is rare, if consciousness depends on a fragile chain of conditions, on stable stars and patient chemistry, and time enough for complexity to unfold, then this moment carries a strange weight. It might mean we are among the last, not the pioneers of a young universe, but the late survivors of an aging one, the observers who arrived after the peak, standing in the dimming hall, trying to understand what just happened. Or perhaps it means something else entirely. Perhaps this timing isn't a coincidence. Perhaps life doesn't emerge at the height of chaos, but after it, when things have had time to settle, when enough stars have lived and died to seed the universe with the elements needed for something more intricate, something self-aware. Perhaps consciousness isn't an early spark. Perhaps it's a late reflection, a way for the universe to look back at itself, to trace the arc of its own story, to recognize, in some quiet sense, that it is changing, that it will not always be as it is now. Maybe we're not late. Maybe we're right on time. In that narrow, fleeting window where the universe is old enough to have made us, and still young enough to be worth wondering about. The stars outside your window are older than you think. Most of them were born billions of years ago, in a universe that was far more active than the one we see today. The bright blue giants scattered across the night sky, those sharp, almost defiant points of light, are the exception, not the rule. They burn fast, live briefly, and vanish within a few million years, ending their lives in violent explosions that outshine entire galaxies. Our own star, the Sun, is quieter, more patient, a middle-aged yellow dwarf, already halfway through its life. In another 5 billion years it will change, slowly at first, then all at once, swelling into a red giant, reaching outward until the inner planets are gone, Earth included. By then, the Milky Way will no longer be alone. It will have merged with the Andromeda Galaxy, their long gravitational dance finally resolved in a collision that reshapes them both. For a brief moment, one last flourish, that merger will trigger a final surge of star formation as gas clouds collide and collapse in brilliant bursts of light. And then, it will settle. The chaos will fade into stillness. The new galaxy, larger, older, more diffuse, will become a vast elliptical cloud of aging stars. Red, yellow, quietly dimming. All of this is unfolding inside a universe that is not still, not stable, but expanding and accelerating outward under the influence of dark energy. The galaxies we see tonight won't always be there. Given enough time, trillions of years, distant galaxies will slip beyond the horizon of observation, not because they've disappeared, but because the space between us and them will stretch too quickly for their light to ever reach us again. They will simply fade from existence as far as any observer can tell. Even the faint afterglow of the cosmic microwave background, the oldest light we can see, the echo of the universe's birth, will be stretched thinner and thinner, redshifted into wavelengths so long they become undetectable, gone. Future intelligences, if they ever arise, will look out into a sky that holds almost nothing. Perhaps only their local group of galaxies, floating in an endless black void. And they will have no evidence that the Big Bang ever happened. No background radiation. No distant galaxies rushing away. No visible trace of a beginning. To them, the universe will appear eternal, static, unchanging. They will not be able to reconstruct the story we have pieced together. And that makes our moment incredibly rare. We are living in a brief, almost perfect window when the universe is old enough to be understood and still young enough to remember. We can see its afterglow. We can measure its expansion. We can watch stars being born and dying across billions of light years. We can trace the curve of cosmic history and place ourselves on it. We are the first generation of humans to know, with any real precision, when we are. And that knowledge carries weight. It means we are not central. It means the universe did not wait for us. It means the stars will outlive us, but not by as much as we once imagined. It means the cosmos is not an eternal stage patiently holding space for the human story. It is a process, a finite unfolding, a one-time event, a brief flare of structure in an ocean governed by entropy. And we are here, not at the beginning of that story, but somewhere in the middle, watching it quietly begin to fade. But there is something else hidden in this realization. Something quieter, harder to name. If the peak is behind us, if the universe is already winding down, then the deeper question isn't just what will happen. It's what has already happened, that we still don't understand. Because the universe at its peak wasn't like the one we see today. It was denser, hotter, more violent, and strangely, more fertile. Galaxies collided more often. Black holes fed more aggressively. Stars lived fast and died spectacularly, scattering heavy elements, carbon, oxygen, iron, into space. The raw ingredients of complexity were everywhere. In some ways, the universe 8 billion years ago may have been more hospitable to the rapid emergence of life than it is now. More chaotic, yes, but also more productive. And that leads to a question that sits right at the edge of everything we know. If the universe was more active, more creative, during its peak, then where is everyone? Where are the civilizations that should have risen during that era? The intelligences that had billions of years more than we've had, to grow, to expand, to leave some trace behind. If we are latecomers, then the golden age should not be empty. It should be crowded, filled with remnants, ruins, signals, something, anything, that hints at minds that came and went long before our star ever ignited. And yet, we hear nothing. This tension, this unsettling absence, has a name: Fermi paradox. The silence is not just noticeable, it's overwhelming. So how do we explain it? Maybe intelligence is far rarer than we imagine. Maybe the same processes that make life possible, supernovae, radiation, cosmic instability, also make it fragile. Maybe planets are constantly reset, sterilized before complexity can take hold. Or perhaps we're not late at all. Perhaps we're early. The first to reach this threshold in our region of the universe. The first to look up and ask these questions. And the silence isn't eerie. It's simply unfinished. A cosmos that hasn't fully woken up yet. Or perhaps it did wake up 8 billion years ago at the height of its activity, and what followed is something we don't yet know how to recognize. Something subtle, something that doesn't announce itself, something we've been looking past. This is where the story truly begins. Not with answers, but with the shape of the question. Not with certainty, but with the realization that we are living inside a specific chapter of a much larger story. One that has a beginning, a middle, and an end. And the middle is already behind us. The fire is going out. And we are here, just in time to watch it dim. But to understand why the universe peaked 8 billion years ago, we have to look closer at what star formation actually is. Because stars are not spontaneous. They don't simply appear when conditions are right. They have to be made. Each one is the result of a fragile negotiation, a battle between opposing forces. On one side, gravity, relentless, patient, pulling gas inward, trying to collapse vast clouds into something dense enough to ignite. On the other side, everything else. Pressure, turbulence, heat, the restless motion of particles resisting compression, radiation from nearby stars, shockwaves from exploding supernovae, and the influence of black holes, feeding and blasting energy back into their surroundings. Star formation is not easy. It is a struggle. A delicate balance that must hold just long enough for gravity to win, just long enough for a cloud of hydrogen to collapse, heat up, and cross the threshold into fusion. And when that balance shifts, even slightly, creation slows. Eventually, it stops. Gravity does win in the end, but only under the right conditions, when the gas is cold enough, dense enough, quiet enough to let gravity do its slow, patient work. In the early universe, those conditions were rare. Everything was too energized, too restless. After the Big Bang, the gas was still hot, so hot that hydrogen atoms couldn't even hold on to their electrons. It existed in an ionized state, a kind of glowing plasma that trapped radiation, absorbed energy, and resisted collapse. Instead of cooling and settling, it stayed agitated, constantly stirred by turbulence, by dark matter structures forming beneath it, by shockwaves rippling outward from the first stars. And those first stars? They were nothing like the ones we see today. Astronomers call them population 30 stars, massive, short-lived, formed from pristine hydrogen and helium. With no heavier elements to help the gas cool efficiently, these stars grew enormous. They burned fiercely and briefly. Within a few million years, many of them were gone, exploding. A single supernova can release, in seconds, as much energy as the Sun will emit over its entire 10 billion-year lifetime. That energy doesn't stay contained, it tears outward, driving shockwaves across light-years of space, heating nearby gas to millions of degrees. In the early universe, that was devastating. Galaxies were small. Their gravity was weak. When these explosions occurred, they didn't just disturb the gas, they could expel it entirely, blowing it out into intergalactic space. Star formation would shut down for millions of years, waiting for fresh gas to slowly fall back in. It was a fragile system, easy to disrupt. But those same explosions were also a turning point, because in dying, those stars created something new. They forged heavier elements, carbon, oxygen, iron, and scattered them into the void. Tiny traces at first, but enough to change the physics of everything that followed. Because heavy elements cool differently. A cloud made only of hydrogen has very limited ways to shed heat. It cools slowly, reluctantly, but introduce carbon, oxygen, atoms with more complex internal structures, and suddenly the cloud can radiate energy far more efficiently. It cools faster. And when gas cools, it collapses. And when it collapses, it forms stars. By the time the universe was a few billion years old, enough of these elements had accumulated. The gas was no longer pristine. It was enriched. It could cool efficiently, collapse more easily, ignite more readily. But it hadn't yet been overworked. It hadn't yet been heated and dispersed by too many generations of stars. It hadn't been stripped away by aggressive feedback. This was the balance. The sweet spot. Galaxies were still small enough to collide frequently, feeding fresh gas into their centers, triggering bursts of star formation. The fuel was abundant. The cooling was efficient. The disturbances manageable. Even the supermassive black holes at the hearts of galaxies were still in check. They hadn't yet grown large enough to dominate their surroundings, to unleash the kind of energy that could shut star formation down entirely. But that wouldn't last. Because growth has consequences. As time passed, the black holes fed and grew. The number of supernovae increased. The cumulative effect of all that energy began to reshape the environment. Gas that had once been cold and dense became hot, diffuse, harder to gather. Star formation began to choke itself. Not all at once, but steadily. The universe didn't run out of hydrogen completely. It lost something more subtle. It lost the conditions that made hydrogen useful. Much of the remaining gas was heated, ionized again, or pushed out into the vast voids between galaxies, regions so empty that gravity could no longer pull the material back together. And without collapse, there are no stars. So the decline began, not because the fuel vanished, but because it could no longer be used. And that's the quiet truth beneath it all. The universe didn't just spend its resources. It changed them into something that can't easily be turned back. At the same time, something even quieter and far more profound was taking hold. The expansion of the universe began to accelerate. Driven by a force we still don't fully understand, dark energy, the cosmos started to stretch itself faster and faster. Unlike matter, unlike radiation, dark energy doesn't gather. It doesn't clump into galaxies or stars. It doesn't build anything. It simply pushes. It pulls space apart from within. And as space expands, everything thins out. The density of matter drops, the distances between particles grow, and the chances of gas finding itself in the right place, at the right density, to collapse into a star begin to fade. So the universe isn't just running out of fuel, it's diluting what remains, spreading it so thin that even when the ingredients are still there, they can no longer come together. This is why the peak is behind us, because the conditions that made it possible were temporary. They required a universe balanced on a knife's edge, old enough to have cooled, enriched, and structured itself, but young enough to still be dense, still rich with cold gas, still capable of gathering that gas into something new. That balance is gone. We've crossed into a different era, an era of diminishing returns, where every new star is harder to form than the last, where galaxies slowly exhaust their reservoirs of cold gas, and what remains is either too hot, too diffuse, or too tightly bound to ever collapse again. The numbers make it undeniable. At its peak, the universe was forming stars at a rate of 10 to 30 solar masses per year per cubic megaparsec. Today, that number has fallen to around 1, a drop of 10, 20, 30 times in just 8 billion years. And the decline isn't slowing. It's accelerating. In another 10 billion years, the rate will fall to 1/10 of what it is now. In 100 billion years, 100th, the curve doesn't level out. It keeps falling, closer and closer to zero, never quite reaching it, but never recovering either. This is not equilibrium. This is transition. A slow shift from brilliance to quiet, from a universe full of activity to one defined by absence. And we are living inside that shift. We are watching the dimming happen in real time. You can see it, if you know where to look, in the color of galaxies. Young galaxies, the ones still actively forming stars, shine blue. That color comes from massive, hot, short-lived stars that burn intensely and die quickly. Old galaxies glow red. Their light comes from smaller, cooler stars, ancient ones that formed long ago and now burn slowly, quietly, with no new stars to replace them. When the Hubble Space Telescope turned its gaze into the deepest parts of the sky, it revealed this transition in a single image. The most distant galaxies, the ones we see as they were billions of years ago, are chaotic, blue, bursting with star formation. The closer ones, galaxies as they exist today, are smoother, redder, more settled, older. You can see the universe aging. And the Milky Way? It sits somewhere in between, still forming stars, especially along its spiral arms where cold gas is compressed and ignited. but also home to vast populations of ancient red stars, quiet witnesses to a more active past. It is middle-aged, past its own peak, which likely occurred around 10 billion years ago when it merged with smaller galaxies. Those mergers brought in fresh gas, triggered bursts of star formation, and helped build the galaxy we see today. But they also had consequences. They stirred the system, fed the central black hole, changed the long-term balance. At the center of the Milky Way lies a Sagittarius A, a supermassive black hole about 4 million times the mass of the Sun. Right now it's quiet, almost invisible. But it won't always be. In a few billion years, when the Milky Way merges with the Andromeda Galaxy, that calm will break. Gas will be funneled toward the center, feeding the black hole. It will ignite, briefly transforming into a quasar, a beacon so luminous it can outshine the entire galaxy. And in doing so, it may seal the galaxy's fate, blowing out the remaining gas, ending star formation, leaving behind a vast, aging structure, slowly fading into the dark. A final flare, before the long silence. This is the future of all galaxies, a final flare of activity, and then, eventually, silence. But that peak we've been tracing, it isn't just something that happens inside galaxies. It belongs to the universe itself. A kind of global high point in the history of structure, of light, of creation. To understand why it happened when it did, you have to zoom all the way back to the beginning. Imagine the universe as a symphony. At first, just noise. In the first fleeting moments after the Big Bang, there was no structure, no rhythm, just a chaotic sea of energy. Temperatures were so extreme that even particles couldn't exist in any stable sense. It was motion without form. But as the universe expanded, it cooled. And slowly, almost imperceptibly, the noise began to resolve. Quarks combined into protons and neutrons. Those fused into the first atomic nuclei. Electrons eventually settled in, forming the first atoms. For the first time, matter could exist in a stable way. Then, gravity took over. Tiny irregularities, subtle fluctuations in density, seeded during the era of cosmic inflation, began to grow. These weren't dramatic differences, just one part in 100,000. But that was enough. Because gravity doesn't need much. A slightly denser region pulls in more matter, which makes it denser still, which pulls in even more. A slow amplification, building over millions of years. Those fluctuations became something larger. Dark matter halos. Invisible scaffolds made of dark matter, shaping where ordinary matter would gather. Hydrogen gas fell into these halos, cooling, clumping, collapsing. And then, the first stars ignited. Not smoothly, not evenly, but in bursts, triggered by collisions, by mergers, by moments when conditions briefly aligned. For the first few billion years, the universe wasn't performing yet. It was building the instruments, galaxies assembling, clusters forming, gas settling into structures that could sustain something more complex. And then, around 5 billion years after the beginning, everything came together. The gas was abundant, the cooling was efficient, the structures were in place, the orchestra was ready, and the universe reached its crescendo. Stars forming at astonishing rates, galaxies glowing with billions of newborn suns, energy, light, and structure at their most intense, their most intricate. This was the peak, not the start of the symphony, but its middle, the moment when all the themes converge, when everything is alive at once. And then, slowly, the sound began to fade, not abruptly, not all at once, but instrument by instrument, fuel depleted, feedback intensified, expansion stretched everything thinner. The same processes that created the music began to quiet it. The symphony is still playing, but now it's softer, simpler. A few lingering notes carrying a melody that once filled the cosmos. And we are here for the final movement, listening to the decrescendo. And that brings us to a question that refuses to go away. If the peak is behind us, if we are living in the decline, then what does that say about us? About intelligence? Are we just an accident? A rare fluctuation that happened to arise in the fading light of a universe past its prime? Or are we something more inevitable? A pattern that only emerges after enough time has passed, after the chaos has settled, after stars have lived and died, after the elements needed for complexity have been forged and scattered? Maybe intelligence doesn't belong to the beginning. Maybe it belongs to the middle, or even the end. Maybe consciousness is what happens when the universe has cooled enough, stabilized enough, to reflect on itself. Not too early, when everything is too violent. Not too late, when everything has gone quiet. But in that narrow, fleeting window in between, the same window we find ourselves in now, there is a quiet idea, rarely stated outright, but hard to ignore once you see it, that intelligence may not belong to the peak at all. Because the peak is too much, too violent, too bright, too unstable. At the height of star formation, galaxies weren't calm, nurturing places. They were chaotic engines of creation and destruction happening at the same time. Stars were forming in furious bursts. Massive ones, short-lived, unstable, filled the sky with intense ultraviolet radiation. Supernovae were frequent. Gamma-ray bursts, rare but catastrophic, could sterilize entire regions of a galaxy in seconds. A planet forming in that environment wouldn't just have to survive. It would have to endure constant interruption. Life, if it began at all, might be erased before it had time to become anything more. The peak, in other words, was not just an age of creation. It was an age of reset. And the two were inseparable. It's only later, after that storm begins to pass, that something different becomes possible. Star formation slows. Galaxies settle. The chaos softens into something more stable. And in that quieter universe, a different kind of star begins to matter. Stars like the Sun, steady, middle-aged, long-lived, not the brilliant, short-lived giants of the peak, but slower burners, reliable, consistent. They form from gas that has already been enriched by earlier generations, full of the heavier elements needed for planets, oceans, chemistry. And just as importantly, they last billions of years, long enough for molecules to assemble, for oceans to form, for life to begin, fail, begin again, for single cells to become complex organisms, for minds to emerge and ask questions. If this idea is right, then everything changes. We are not late. We are exactly on time. The universe had to burn through its most chaotic phase before it could make something like us. It had to live fast before it could slow down enough to reflect. We are not a coincidence of the decline. We are a product of it. The universe, in a sense, needed to age before it could become aware of itself. And that is a strange, humbling thought. It means the golden age, the time when the cosmos was at its brightest, most productive, may have been the least hospitable to minds. It means consciousness is not an early spark, but a late emergence. That the dimming of the stars, the slowing of creation, isn't just an ending. It's also a beginning, the condition that makes us possible. And yet even this isn't certain. The data is clear. The curve is real. The peak happened. But what it means is still open. There are other ways to see it, other frames that shift the emotional weight without changing the underlying truth. Because there's one more possibility, one that stretches the idea even further. What if the curve we see isn't the whole story? What if it's only local? Everything we've measured, every galaxy, every star formation rate, is confined to what we can observe. A vast region, yes, but still limited. a sphere about 90 billion light-years across, defined by how far light has been able to travel since the Big Bang. But beyond that, there is more. Possibly much more. During cosmic inflation, space expanded faster than light itself, stretching the universe to scales far beyond what we will ever be able to see. The observable universe may be just a tiny fragment of a much larger, perhaps infinite, whole. And if that's true, then different regions of the universe could be living through different moments in their own history. Some might be peaking right now. Some may have peaked long before our region ever formed. Others might not reach their peak for trillions of years. The curve we've measured, the rise and fall of star formation, would still be real, but it would be our curve, a local story, one piece of a much larger mosaic, a universe not defined by a single timeline, but by countless overlapping ones, some young, some old, some just beginning, while others are already fading into silence. And here we are, in one particular patch of that vast, unknowable whole, trying to understand where we stand and what it means. This idea, sometimes called the patchwork universe, has a certain quiet comfort to it. It softens the feeling that we've arrived too late. Because if the cosmos is vast enough, if it extends far beyond what we can ever see, then somewhere, beyond our horizon, the golden age may still be unfolding. Stars igniting in frantic waves, galaxies colliding in brilliant bursts, perhaps even minds awakening in those distant regions, looking up at a sky far more alive than ours. A universe still in full bloom. But that comfort comes with a cost, because if the universe is a patchwork, then we are trapped in our piece of it, confined to our local region, our supercluster, our observable bubble. Everything beyond that boundary isn't just far away, it's unreachable. The expansion of space, driven by dark energy, ensures that regions beyond a certain distance are receding faster than light itself. Not moving through space, but carried by the stretching of space, which means no signal, no particle, no information from those regions can ever reach us. They are not just distant, they are permanently cut off. And that is one of the quiet cruelties of cosmology. The universe is larger than we can ever know. And the part we can know is shrinking. Over immense stretches of time, galaxies now visible at the edge of our horizon will simply fade away. Not because they've disappeared, but because their light will never arrive. In 100 billion years, an observer in the Milky Way, or whatever it becomes after merging with its neighbors, will look out into a sky that feels eerily empty. Only a handful of galaxies will remain visible. A small, gravitationally bound group, surrounded by darkness. The ancient afterglow of the cosmic microwave background will have stretched into wavelengths so long they can no longer be detected. Gone. The distant galaxies that allowed us to measure expansion, to infer dark energy, to reconstruct the rise and fall of star formation will no longer be there. Not because they ceased to exist, but because the universe expanded them out of reach. Future astronomers, if they exist, will inherit a profoundly different sky. They will see no evidence of the Big Bang, no expanding universe, no cosmic background radiation, no distant galaxies racing away. To them, the universe will appear static, eternal, unchanging. A small island of stars in an infinite void. They will be cosmologically blind, prisoners of their moment in time, unable to reconstruct the history we have painstakingly uncovered, simply because the evidence will have been erased. And that makes this moment extraordinary. Not the peak, but a narrow fleeting window where the peak is still visible in the data, where the scars of the beginning are still etched across the sky, where the universe is old enough to be understood and still young enough to be observed. That window is closing. Slowly, quietly, on timescales beyond human intuition. But closing nonetheless. The light is fading, The evidence is receding, and we are here, right now, in the brief moment when the whole story is still within reach. And yet, even this might not be the full picture. There is another possibility, a more unsettling one. What if the peak isn't behind us? What if what we're seeing isn't the decline of the universe, but the limit of our ability to measure it? Because measuring star formation across cosmic time is not simple. It's an inference. We don't watch stars being born directly, we estimate their birth rates from the light they emit. Ultraviolet radiation from young stars stretched into optical or infrared wavelengths by expansion. Signals that must be carefully interpreted, corrected, modeled. Dust complicates everything, absorbing light, hiding activity, re-emitting energy in ways that can mislead us. And our models, our assumptions about how stars form, how massive they are at birth, how long they live, introduce uncertainties we can't completely eliminate. Even something as fundamental as the initial mass function, the statistical pattern of how stars are born, might not be constant across all time and environments. If any of these assumptions shift, even slightly, the curve we've drawn, the rise and fall of star formation, could change. Not dramatically enough to erase the trend, but enough to remind us of something important. We are not outside the universe, observing it perfectly. We are inside it, limited. Interpreting distant light through imperfect instruments, building a story from fragments. And that means, even now, with all we know, there is still room for uncertainty. Still room for the possibility that the story is more complex than it appears. That the curve we see is real, but not complete. Every step in this reconstruction carries uncertainty. And those uncertainties don't just sit quietly, they compound. A small miscalibration in how we translate light into star formation rates, a slight bias in the galaxies we sample, an assumption in our models that turns out to be incomplete, all of it can ripple outward. Shift the peak. Flatten the curve. In extreme cases, even reshape the story we think we're seeing. The data points toward a peak around 8 billion years ago. But the data is not perfect. It never is. It's drawn from fragments, distant galaxies we can barely resolve, signals filtered through dust and time, interpreted through models that, however sophisticated, still simplify something unimaginably complex. This doesn't mean the peak is an illusion. The evidence is strong. Multiple independent surveys, using different methods, converge on the same broad picture, a rise, a crest, a decline. But it does mean something important. Certainty in cosmology is always provisional. We are reconstructing the history of the entire universe from a single vantage point at a single moment in time with instruments that can only see so far. We are, in a sense, cosmic archaeologists, trying to rebuild a civilization from scattered fragments. Except the civilization is everything that has ever existed, and the fragments are photons that have traveled billions of years just to reach us. So the peak might be real, or it might be slightly misplaced, or it might be real, but not what we think it is. A feature that looks like a peak from where we stand, but would look different from another epoch, another region, another framework entirely. And strangely, this uncertainty doesn't weaken the question, it sharpens it. Because even if the curve is imperfect, even if our interpretation evolves, the deeper fact remains. We are able to ask the question at all. We are living in a time when the universe can be studied, when its past is still visible, when evidence hasn't yet slipped beyond reach. That alignment is not guaranteed. It depends on a fragile chain of conditions, a stable star like the Sun, a rocky planet at just the right distance, an atmosphere rich enough in oxygen to support complex life, a climate stable over millions of years, a species capable of building telescopes, satellites, computers, of asking why. None of this belongs to the peak. These are products of the decline. They are features of a universe that has cooled, settled, matured. The peak, if it is real, is something we can observe, but could never have inhabited. The decline is something we can inhabit, but cannot escape. And so the question shifts, not which era is better, but what it means to exist in the narrow space between them, in the moment where the universe is still understandable, but already fading. You've heard the phrase, "You are made of star stuff." It's true, but it's more precise than that. You are made from the ashes of stars that died long before the sun ever formed. Carbon, oxygen, nitrogen, elements forged in stellar cores, then scattered into space by supernovae during a more active era of the cosmos. Those stars lived during or near the peak. They burned. They died. They gave their material back to the universe. That material cooled, condensed, became new clouds, new stars, new planets. One of those planets was Earth. One chain of chemistry on that planet became life, and one branch of that life became you. You are not just made of star stuff. You are made of time, of a universe that had already lived through its most intense phase, and softened into something capable of sustaining complexity. You are a consequence of the decline. You exist because the universe has already spent most of its fuel, because the chaos has quieted, because stability, fragile, temporary stability, became possible. And that leads to one final, almost unsettling thought. You are the universe looking back at its own youth, tracing the curve of its own history, trying, through you, to understand what it once was, and what it is becoming. And what it is becoming is colder, darker, quieter. Not in your lifetime, not in 1,000 lifetimes, but on the timescales that matter to stars, to galaxies, to the universe itself, the direction is unmistakable. Star formation is declining. Gas is heating, thinning, drifting out of reach. Galaxies are pulling away from one another. The universe is not cycling. It does not refresh. It is running down, and there is no hidden mechanism waiting to wind it back up. That isn't an easy truth to sit with. It runs against something deep in us, the idea that the future should be brighter, fuller, better than what came before. That progress is a universal law. But the cosmos doesn't follow our stories. In some fundamental sense, the past was brighter, more active, more alive with possibility. And what we see now is the long echo of that intensity. The night sky, breathtaking as it is already a diminished version of what once existed. And the skies to come will be dimmer still. But discomfort is not the same as despair. Knowing that the universe has peaked doesn't strip life of meaning, it sharpens it. It tells us something simple but profound. The universe is not infinite in event. It has a shape, a beginning, a middle, and an end. And we are here now inside one specific chapter of that shape. The stars are not eternal. The cosmos is not a fixed stage. Everything you see is part of a process, one that began long before us and will continue long after we are gone. And that changes the question. Because if the universe has a story, then when you exist becomes just as important as where. Timing matters. It always has. And if we want to understand our place in all of this, we have to understand the curve we're living on, the rise and fall of star formation, the peak behind us, the silence ahead. To understand the peak, we have to go further back before the light, back before stars, back to what cosmologists call the Dark Ages, Not the human dark ages, but the cosmic ones. The long stretch after the Big Bang, when the universe had cooled enough for atoms to form, but not enough for stars to ignite. It was a time of quiet, of cold hydrogen gas filling space. No galaxies, no stars, no light, except the fading afterglow of the beginning itself. A universe full of matter, but empty of illumination. This period lasted for hundreds of millions of years, and it's one of the hardest chapters of cosmic history to study, because it left almost no direct trace. No bright signals, no obvious markers, just a gap. A blank page we've had to reconstruct through theory, simulation, and the faintest indirect clues. But within that silence, something essential was happening. The foundations were being laid. During this time, the universe was dominated by something we still cannot see directly. Dark matter. It doesn't emit light. It doesn't absorb light. It doesn't interact with ordinary matter in any familiar way. And yet, it shapes everything, because it does respond to gravity. And more importantly, it creates it. Unlike ordinary matter, dark matter wasn't slowed by radiation or heat. It could begin clumping early, forming invisible structures, gravitational wells, long before normal gas could settle. These structures, dark matter halos, became the scaffolding of the universe. Hydrogen gas, still diffuse and quiet, began to fall into them. Slowly, gradually, inevitably. Without dark matter, none of this would have happened. No galaxies, no stars, no structure at all. Just a uniform, expanding fog of hydrogen, stretching endlessly, doing nothing. But because of it, the universe had a framework, a hidden architecture, a way for matter to gather, to collapse, to eventually ignite. And from that quiet, invisible beginning, everything else followed. Dark matter built the scaffolding. Ordinary matter filled it in. Over tens of millions of years, hydrogen gas drifted into those invisible wells, falling, colliding, compressing, heating as gravity pulled it inward. And in the densest pockets, something extraordinary finally happened. The gas ignited. The first stars were born. They were nothing like the sun. These were giants, hundreds of times more massive, burning fiercely, radiating intense blue light. They consumed their fuel at a staggering pace, living only a few million years before collapsing or exploding as supernovae, some leaving behind the first black holes. Brief lives, violent deaths. But their impact was enormous. Their light began to tear apart the darkness itself. The radiation they emitted ionized the surrounding hydrogen, ripping electrons from protons, transforming neutral gas into a glowing, energized plasma. Around each star, a bubble of ionized space expanded outward. And then those bubbles began to overlap, to merge, to spread, until, slowly, the entire universe was transformed. This was the epoch of reionization, a turning point roughly between 200 million and 1 billion years after the Big Bang. The end of the cosmic dark ages. The beginning of a universe filled with light. But even then, the peak had not yet arrived, because the first stars, powerful as they were, weren't enough. They were too rare, too scattered, too short-lived to sustain the kind of ongoing, large-scale creation needed to push the universe to its maximum. What the universe needed next was structure. It needed galaxies. Galaxies formed through accumulation and collision. Small structures merged into larger ones. The earliest galaxies were tiny dwarf systems with only a few million stars. But they didn't stay small for long. They collided. They merged. They grew. Each collision brought in fresh gas. And that gas, compressed by the violence of the merger, ignited in bursts of star formation, intense, chaotic, but incredibly productive. By a billion years after the beginning, the universe was filled with these small, irregular galaxies, each one a storm of activity. Each one interacting with its neighbors, in a constant gravitational dance. But they didn't look like galaxies today. They were dense, compact, turbulent. Stars formed in massive clusters, not in the elegant spiral patterns we see in the Milky Way. Their gas was still relatively metal-poor, only lightly enriched by earlier generations of stars, so cooling was less efficient, and star formation happened in larger, more chaotic bursts. At their centers, black holes were already forming, already growing. But they weren't yet dominant. They hadn't reached the scale where they could regulate, or suppress, the entire galaxy. So the system remained open, unrestrained, still building. This was the setup, the universe assembling itself, piece by piece, constructing the conditions that would eventually allow for something more sustained, more balanced, more efficient. Because the peak required alignment. Not just activity, but the right kind of activity. It required a vast supply of gas, still abundant, not yet depleted. Efficient cooling, enabled by heavier elements forged in earlier stars. Frequent galaxy interactions to compress gas and trigger star formation. And feedback from stars and black holes that was present, but not yet overwhelming. All of those conditions had to exist at once. And they did. For a brief moment, around 5 billion years after the Big Bang, the balance was nearly perfect. The universe had cooled enough for gas to settle into galaxies more easily, but was still dense enough for those galaxies to collide often. The gas had been enriched, enough to cool rapidly and collapse into stars, but not so much that it had been heated or expelled beyond use. And the central black holes? They were there, growing, but not yet powerful enough to shut everything down. So for that brief window, everything aligned, and the universe reached its peak. This was the Golden Age, a time when galaxies blazed with activity, forming stars at rates 10, 20, even 30 times higher than today. Every region of space was richer, denser, more alive with possibility. Gas clouds collapsed constantly. New suns ignited in staggering numbers. If you could have stood on a world in one of those galaxies, the sky would not feel quiet or sparse, it would feel crowded. Brilliant blue stars, massive clusters, entire regions glowing with the light of ongoing creation. It wasn't just brighter. It was overwhelmingly alive. But that intensity carried a hidden cost, because every star that formed also pushed the universe one step closer to slowing down. Massive stars burned fast and died violently. Their supernovae didn't just create elements, they blasted gas outward, heating it, dispersing it, making it harder for the next generation of stars to form. Smaller stars lived longer, but in doing so, they locked away hydrogen that could have fueled future creation. And at the centers of galaxies, supermassive black holes were growing, fed by the same gas that formed stars. As they grew, they began to push back. Jets, radiation, winds, all of it heating the surrounding gas, preventing it from cooling and collapsing again. Creation was feeding its own limits. By about 8 billion years after the Big Bang, the balance had shifted. The gas supply was thinning, feedback was strengthening, and star formation, once unstoppable, began to slow. At first, gently, then unmistakably. The expansion of the universe, driven by dark energy, made things worse. As space stretched, matter spread out. Gas became harder to gather. The raw ingredients were still there, but no longer in the right form. The peak had passed. The decline had begun. That is the standard story, and it fits the data well. But it's not the only way to read the curve, because what looks like a universal decline might also be a shift. One possibility is that the peak isn't the universe slowing down, it's the universe changing gears. In the early cosmos, star formation was dominated by small, irregular galaxies, dwarf systems that formed stars in bursts. They were numerous, efficient, and chaotic, individually faint, but collectively responsible for much of the star formation at the peak. Over time, those dwarfs merged, building larger systems like the Milky Way. But large galaxies behave differently. They have more gas, but also more gravity, stronger feedback, larger black holes, hotter halos, all of which make star formation less efficient. So the universe didn't necessarily stop forming stars. It just started doing it, more slowly, in different places, under different rules. Another possibility is more dramatic, but also more temporary. Star formation might flare up again. When galaxies collide, we know, for example, that the Milky Way is on a slow collision course with the Andromeda Galaxy. When they merge, billions of years from now, the interaction will compress gas, trigger starbursts, and briefly revive intense star formation. For a moment, the universe will seem young again, but only locally, only briefly. Because those bursts don't solve the larger problem, the total supply of cold gas is still shrinking, and nothing replenishes it fast enough. So even these final flares are just echoes, short-lived resistances against a long, irreversible trend. And then there is a third idea, more subtle, but just as intriguing. What if the peak depends on how we define a star? Right now, we draw a line. A star must be massive enough to fuse hydrogen in its core, about 8% the mass of the Sun. Below that, we call them brown dwarfs, failed stars. But they still form. And they still will form as long as gas exists, because they require less mass, less pressure, less extreme conditions. They are easier to make. And they last a very long time. If you widen your definition, if you include these dim, slow-burning objects, the story changes slightly. The universe may not be shutting down completely. It may simply be transitioning from bright, energetic stars to faint, long-lived ones, from brilliance to persistence, not an end of formation, but a soft fading into a quieter mode of existence. And maybe that's the deeper pattern, not a sudden ending, but a gradual shift in what the universe is capable of producing. From the spectacular to the subtle, from explosive creation to quiet endurance, and somewhere within that transition, we exist. If we widen the definition of what counts as creation, the story begins to soften, not contradicting what we see, but reframing it. Because if we include brown dwarfs, even large planets, then the universe may not be declining as sharply as it appears. It may be shifting from an era dominated by massive, luminous stars to one filled with smaller, quieter objects. From brilliant blue giants to dim red dwarfs and fading embers. From a universe defined by light to one defined by faint heat, by long-lived glow, by persistence rather than intensity. This doesn't make the cosmos brighter. A universe full of low-mass stars and brown dwarfs would still feel dark to us, almost empty by comparison. But it suggests something deeper. The process of making structure may continue far longer than the light would lead us to believe. Gravity doesn't stop working. Gas doesn't instantly vanish. It just becomes harder to gather, slower to collapse, quieter in what it produces. So the universe may not run out of creative potential as quickly as we assume. It may simply become harder to notice, less dramatic, more subtle. And that changes the feeling of the peak, even if it doesn't change the fact. Because no matter how we interpret it, one truth remains. The universe was more active 8 billion years ago. It is less active now. It will be less active still. Whether we call that a decline, a transition, or a change in creative mode, the trajectory holds. The cosmos is winding down. But trajectories can be deceptive. What looks like a straight descent from one angle can reveal itself as something more complex from another. What feels like an ending might also be a transformation. A movement from one kind of existence to another. From chaos to order. From noise to signal. From the explosive creativity of youth to the deliberate, patient construction of age. And this is where the question stops being purely scientific and becomes philosophical. Because the peak is not just a feature in the data. It reflects what we value. If we value brightness, energy, luminosity, spectacle, then yes, the peak was the golden age, and we are living in the decline. But if we value complexity, then the story shifts. Because complexity doesn't come from intensity alone, it comes from time, from the slow accumulation of structure, from systems that learn to store energy, process information, resist entropy, at least for a while. Stars are bright, but they are simple. Planets are dim, but they are structured. Life is dimmer still, almost invisible in the universe's total energy budget, and yet incomparably more intricate than any star. By that measure, the universe may not be declining at all, it may just be beginning. The peak of star formation might mark the height of raw energy output, but not the height of organization, not the height of information, not the height of meaning. Those peaks might still be ahead. Or they might be happening right now, in rare, scattered pockets like this one. Or they might be fundamentally unmeasurable, because complexity doesn't scale the way energy does. It doesn't spread evenly across space. It concentrates in unlikely places, under fragile conditions, in systems that are almost invisible to the tools we use to study the cosmos. We can count stars, but we cannot count minds. We don't yet know what a mind even means at cosmic scale. We can measure light, but we cannot measure meaning, because meaning doesn't exist independently. It emerges from relationships, from context, from observers, from beings capable of asking questions like this. And so, we find ourselves in a strange position. We can map the rise and fall of stars with astonishing precision, yet remain almost completely blind to the rise and fall of the very thing asking the question, which means the most important curve of all. The curve of awareness, of intelligence, of meaning, might be the one we cannot see. The one we are inside of, the one we are, perhaps, helping to write. What we do know is that we are here, now, in an epoch of the universe that is less bright than it once was, but more structured, more organized, more capable of producing systems that can ask questions and seek answers. We are a product of the decline, but we are also a product of the accumulation, the slow buildup of complexity that the decline makes possible. The stars are fading, but the questions are sharpening. The gas is dispersing, but the information is concentrating. The universe is cooling, but it is also waking up, becoming aware of itself through minds that evolved on planets orbiting stars that formed from the ash of earlier generations. This is not a narrative of decline. It is a narrative of transformation. The universe is not dying. It is changing, and we are part of that change. Witnesses and participants both. Observers of the curve and points on the curve. Watchers of the fire and sparks thrown from the fire. The peak is behind us. The silence is ahead. But between the peak and the silence is this moment, this narrow window when the universe can be known. And we are the ones doing the knowing. There is a specific day in the history of cosmology when the reality of the peak became undeniable. When the measurements converged and the models aligned and the curve was drawn with enough precision that doubt became difficult. It was not a single discovery but an accumulation, a decade of observations from Hubble and ground-based telescopes, surveys with names like Goods and Candles and deep-field images that captured thousands of galaxies across billions of years of cosmic time. The astronomers analyzed the light, corrected for dust and redshift, built models of stellar populations, and plotted the results. The curve emerged, a rise in the first few billion years, a peak around 5 to 6 billion years after the Big Bang, and then a steady decline continuing to the present day. There was no press conference, no dramatic announcement. The result appeared in a series of papers published in the early 2000s and refined over the following decade. The language was careful, hedged with uncertainties and caveats, as all scientific language is. But the conclusion was clear. The universe had peaked. We were living in the aftermath. One of the astronomers who contributed to these measurements later described the feeling of seeing the curve for the first time as disorienting. Not because it was unexpected, but because it made the universe feel old in a way that the abstract knowledge of its age did not. 13.8 billion years is a number, large but emotionless. A curve is a story. It has a shape, a beginning, a middle, an end. Seeing the curve made the universe feel finite, mortal, like something that could be exhausted. This astronomer, whose name does not matter because the insight belongs to everyone who has looked at the data, said that after seeing the curve, they found it difficult to look at the night sky the same way. The stars were no longer eternal. They were remnants, afterimages, echoes of a time when the universe was louder. The Milky Way, sprawled across the sky like a river of light, was not a sign of abundance, but of scarcity, a concentration of what little light remained in a cosmos growing darker. This is the emotional cost of cosmology. It is not nihilism, it is perspective. It is the recognition that the universe does not revolve around us, that it was not made for us, that it will continue long after we are gone, and that continuation will be quieter, colder, emptier than what we see now. But perspective cuts both ways. If the stars are temporary, then they are also precious. If the universe is finite, then every moment of it matters in a way that infinity does not permit. If we are living in the decline, then we are also living in the only time when beings like us can exist. In the narrow window, when the cosmos is old enough to create complexity, but young enough to still be lit. The astronomer did not stop looking at the sky. They looked harder, with more attention, with the knowledge that what they were seeing would not last, that the curve was still falling, that the light was still fading, and that their work, the work of measuring and understanding and mapping the decline, was itself a rare and temporary thing. A collaboration between human minds and the photons that had crossed billions of light years to reach them. This is what it means to live after the peak. Not despair, but urgency. Not meaninglessness, but specificity. The universe is not eternal, and neither are we, and the alignment of our brief existence with the tail end of the cosmic golden age is a coincidence, or a necessity, or a mystery we have not yet solved. Let the curve sit with you for a moment. The rise, the peak, the fall, the universe at its brightest 8 billion years ago. The universe today, dimmer. The universe in the future, dimmer still, until the last star forms, the last galaxy fades, and the cosmos is filled with the slow decay of black holes radiating into the void. The timescale of this process is incomprehensible. Trillions of years. Quadrillion, numbers so large they cease to mean anything, except as markers of duration, placeholders for the idea that the universe will continue long after it has stopped doing anything interesting. But you are not living trillions of years from now. You are living now, in the era when stars still form, when galaxies still collide, when the cosmic microwave background is still visible and the evidence of the Big Bang is still accessible. You are living in the decline, but the decline is not yet the end. It is the long middle, the slow fade, the decrescendo that will last longer than the crescendo did, but will eventually resolve into silence. Your body is made of atoms forged in stars that contributed to the peak. The carbon in your cells was created in the core of a red giant that lived and died billions of years ago, when star formation rates were higher and the universe was denser. That star fused helium into carbon, layer by layer, until its core was iron and it could fuse no more. Then it collapsed and exploded, scattering its carbon into space, where it cooled and condensed into a new generation of stars and planets. One of those planets was Earth. One lineage of carbon-based chemistry became you. You are stardust, but you are also a specific kind of stardust. The kind that could only form after the peak, after enough generations of stars had lived and died to enrich the universe with the heavy elements that make biochemistry possible. The first stars were pure hydrogen and helium. They could not have made planets like Earth. They could not have made life like you. The peak was necessary, not as a destination, but as a process, a phase in the evolution of the cosmos that created the conditions for what came next. This is the other side of the decline. It is not just loss. It is also inheritance. The universe gave everything it had during the peak, burned through its fuel, scattered its wealth across space, and what remains is the product of that expenditure. You are the product. Every breath you take, every thought you think, every photon your eyes absorb is a consequence of the peak and the decline, of the universe spending itself and leaving behind the fragments from which new forms of complexity can emerge. The peak was bright but sterile. The decline is dim but fertile. This is the trade. This is the shape of cosmic time. Yet there is a competing theory, one that challenges the entire narrative of the peak and the decline, that suggests we are not measuring what we think we are measuring. This theory begins with a simple observation. Star formation is not the only way the universe creates structure. Stars are one phase of a larger process, a process that includes planets, asteroids, comets, dust, gas, black holes, neutron stars, white dwarfs, and forms of matter we have not yet discovered. When we measure star formation rates, we are measuring the rate at which hydrogen is being converted into helium in the cores of collapsing clouds. But we are not measuring the rate at which structure is being created overall, because much of that structure is invisible to the techniques we use. Consider planets. They form around stars, condensing from the disk of gas and dust left over after the star itself has formed. But planet formation does not end when the star dies. Planets can survive the death of their star, orbiting as cold remnants in the dark. They can be ejected from their systems and wander through space as rogue planets, invisible and uncounted. Some estimates suggest there are more rogue planets in the galaxy than there are stars, but we have detected only a handful, because they emit no light and can only be seen when they pass in front of a more distant star and bend its light through gravitational lensing. If planets are being created at a rate comparable to or greater than stars, and if most of those planets are invisible, then the decline in star formation might not reflect a decline in the creation of structure. It might reflect only a decline in the creation of luminous structure. A shift from a universe dominated by bright objects to a universe dominated by dark objects, from stars to planets, from light to shadow. This theory, sometimes called the dark structure hypothesis, is difficult to test because dark objects are difficult to detect. But it suggests that the curve of star formation is not the curve of cosmic creativity. It is only the curve of cosmic brightness. And brightness, while easy to measure, is not the same as importance. A universe filled with rogue planets and brown dwarfs and cold clouds of gas is a universe still capable of complexity, still capable of creating systems that process information and resist entropy, even if those systems do not shine. There is another layer to this theory, More speculative, but no less intriguing. If intelligence can arise on planets around stars, then it might also arise on rogue planets heated by internal processes, by the decay of radioactive elements or the residual heat from their formation. Such planets would be invisible to our telescopes, but they could host ecosystems, civilizations, technologies. They could be the dominant form of life in the universe, far more numerous than the life that arises on planets around stars. Because rogue planets are not constrained by the habitable zone, the narrow range of distances from a star where liquid water can exist on the surface. A rogue planet could maintain liquid water beneath a thick ice shell, heated from below by geothermal energy, the way Europa and Enceladus do in our solar system. Such an ocean could host life, and that life could evolve into intelligence, and that intelligence could build civilizations that have no concept of stars, that live entirely in the dark, that measure time not by the rising and setting of a sun, but by the slow decay of heat, the gradual cooling of their world over billions of years. If this is true, then the decline in star formation is irrelevant to the question of life and intelligence in the universe. The peak was the peak of light, but the peak of mind might still be ahead, or it might be distributed across time in a way that our current measurements cannot capture. Because we are looking for light, and minds do not require light. This is a radical reframing of the curve. It does not deny the measurements. It accepts that star formation has declined. It simply denies that star formation is the metric that matters. It suggests that the universe is transitioning from a phase dominated by stars to a phase dominated by planets and other dark structures, and that this transition is not a decline but an evolution, a movement toward forms of complexity that are quieter, darker, harder to see, but no less real. The evidence for this theory is thin. We do not yet have the technology to detect rogue planets in large numbers, let alone determine whether any of them host life. But the logic is compelling. Stars are wasteful. They burn through hydrogen at a furious rate, converting mass into light and heat, most of which radiates into empty space and does nothing. Planets are efficient. They conserve energy, radiate slowly, last longer. A universe that transitions from stars to planets is a universe that is learning to do more with less, to stretch its finite resources across longer timescales, to prioritize complexity over brightness. By this measure, the decline is not a tragedy. It is a maturation. The universe is growing up, moving from the reckless energy expenditure of youth to the careful resource management of age. The peak was adolescence, all flash and fury. The decline is adulthood, quieter but wiser, dimmer but deeper. But even this interpretation has a flaw. It assumes that complexity is the goal, that the universe is moving toward something, that the curve has a purpose. But the universe does not have goals. It does not optimize. It simply unfolds according to the laws of physics, and those laws do not care about complexity or intelligence or meaning. They care about entropy, about the dissipation of energy, about the gradual smoothing of differences until nothing remains but a uniform, lifeless equilibrium. The second law of thermodynamics is undefeated. Entropy always increases. Energy disperses. Structure dissolves. The universe is not moving toward greater complexity. It is moving toward greater disorder, and any pockets of complexity that arise along the way are temporary, local, doomed. This is the counterclaim, the dark mirror of the maturation hypothesis. It says that the decline is exactly what it looks like: a winding down, a dissipation, an irreversible slide toward heat death. The peak was an anomaly, a brief spike of order in an ocean of chaos, and the decline is the return to baseline, the reassertion of entropy's dominance. Complexity is not the destination. It is a detour, a statistical fluctuation, a pattern that emerges and dissolves and leaves no trace. If this is true, then the universe is not maturing. It is dying. The stars are fading not because they are being replaced by something better, but because the fuel is running out and there is no alternative. The planets, the brown dwarfs, the cold clouds of gas, they are not the next phase of cosmic evolution. They are the debris, the leftovers, the remnants of a process that has already exhausted itself. This is the bleakest interpretation of the curve, the one that offers no consolation, no hidden meaning, no redemptive twist. It is also the one most consistent with the laws of physics as we currently understand them. Entropy wins. The universe cools. Structure dissolves. The end is silence. But even this is not the final word. Because the laws of physics as we currently understand them are incomplete. We do not know what dark matter is. We do not know what dark energy is. We do not know whether the universe will expand forever or eventually collapse. We do not know whether there are other universes, other dimensions, other laws of physics that apply beyond the horizon of our observations. We do not know whether consciousness is a quirk of chemistry or a fundamental feature of reality. We do not know whether the curve of star formation is the only curve that matters, or whether there are other curves, other metrics, other ways to measure the vitality of the cosmos. We do not know, and the not knowing is important. It is the gap where new theories can emerge, where the data can surprise us, where the universe can turn out to be stranger and richer than we imagined. The peak is real. The decline is real. But the meaning of both is still open, still contested, still subject to revision as we learn more. And we are learning more. Every year, new telescopes come online. New surveys are completed. New data streams in from distant galaxies and nearby planets and the cosmic microwave background. Every year, the picture sharpens, the uncertainties narrow, the curve becomes more precise. But precision is not the same as understanding. We can measure the decline to 3 decimal places and still not know what it means. Still not know whether it is a tragedy or a transition, a death or a transformation. What we do know is that the question matters. That the curve is not just a feature of the data, but a feature of existence. A shape that encompasses everything from the birth of the first stars to the last thought of the last mind. That we are somewhere on that curve, living through it, shaped by it, trying to understand it from the inside. The universe peaked 8 billion years ago. We are living in the collapse. But the collapse is not instantaneous. It is slow, measured in billions of years, and within that slow collapse is room for stars, for planets, for life, for minds, for questions, for the search for answers. The fire is going out, but it has not gone out yet. There is still light, there is still time. And in that light, in that time, we are here, watching, measuring, asking what it means to live on the downslope of the cosmos, what it means to be aware of the curve, what it means to exist in the aftermath of the peak and the prelude to the silence. This is not the end of the story. It is the middle. And the middle is where we live. The search for other intelligences in the universe takes on a different character when viewed through the lens of the peak. If we are living in the decline, and if the peak was the era of maximum star formation, then the peak was also, potentially, the era of maximum planet formation, maximum opportunities for life, maximum chances for intelligence to arise. Which means that if intelligence is common, if it arises wherever conditions permit, then the universe should be crowded with civilizations that emerged during or shortly after the peak. Civilizations that have had billions of years longer than us to develop, to spread, to leave marks on the cosmos. The fact that we see no such marks is called the Fermi paradox, and it is one of the deepest puzzles in science. If the universe is vast and old, If planets are common and life is chemically plausible, if intelligence is even remotely probable, then where is everyone? Why is the sky silent? Why have we detected no radio signals, no megastructures, no evidence of engineering at the scale of stars or galaxies? Why does the universe appear empty of minds other than our own? The peak sharpens this paradox. If star formation was 10 times higher 8 billion years ago, and if the number of planets scales with the number of stars, then there should have been 10 times as many opportunities for life to arise during the peak as there are today. If intelligence emerged on even a tiny fraction of those planets, then the universe should be teeming with ancient civilizations. Civilizations that have had billions of years to expand, to colonize, to reshape the cosmos according to their needs and desires, and yet we see nothing. The galaxies we observe, even those from the peak era, show no signs of large-scale engineering. The stars burn according to the laws of physics, not according to the designs of minds. The cosmic microwave background is uniform, featureless, exactly what you would expect from a universe shaped only by gravity and thermodynamics, with no hint of interference from intelligence. There are many proposed solutions to the Fermi paradox, and the peak adds weight to some while undermining others. One solution is that intelligence is extraordinarily rare, that the chain of events required to go from chemistry to consciousness is so improbable that it has happened only once in the observable universe. And we are it. If this is true, then the peak is irrelevant. It does not matter how many stars formed or how many planets, because none of them, or almost none of them, produced minds capable of asking questions about the cosmos. This solution is called the rare Earth hypothesis, and it is both humbling and terrifying. Humbling because it suggests we are alone, the only witnesses to the universe, the only minds capable of understanding it. Terrifying because it suggests we are fragile, that if we fail, if we destroy ourselves or are destroyed by an external event, then the universe loses its only observer, its only source of meaning, and it will continue for trillions of years without anyone to know it exists. Another solution is that intelligence is common but short-lived, that civilizations arise frequently but destroy themselves within a few centuries of developing technology, either through war, environmental collapse, or some other existential catastrophe. If this is true, then the peak might have produced billions of civilizations, but none of them lasted long enough to spread across the stars, to leave marks we could detect. They flickered into existence and winked out, leaving no trace except perhaps a few radio signals that have long since faded into the noise of the cosmos. This solution is called the Great Filter, and it suggests that somewhere in the chain from chemistry to spacefaring civilization, there is a step so difficult that almost no one makes it through. Either that step is behind us, in which case we are lucky to exist, or it is ahead of us, in which case we are doomed. The peak complicates the Great Filter. If civilizations arise and die quickly, then the peak should have produced a pulse of activity, a brief era when the universe was full of signals and then went silent as each civilization failed. If that pulse occurred 8 billion years ago, then the signals would have long since passed us, traveling outward at the speed of light, unreachable and undetectable from our current position. We would be living in the silence after the pulse, in a universe that was once full of voices but is now empty. Or perhaps the Great Filter is not destruction, but transformation. Perhaps civilizations do not die but transcend, moving beyond the physical, beyond the need for matter and energy, into forms we cannot recognize or detect. Perhaps the peak produced billions of such transcensions, and the universe is full of post-biological intelligences that exist in dimensions or states we have no access to. They are here, all around us, but we cannot see them because we are still bound to matter, to planets, to the slow speed of chemistry and biology. This solution is speculative, untestable, and profoundly strange, but it fits the data as well as any other. The universe appears empty, but perhaps it is only empty of the kinds of intelligence we know how to look for. A third solution, darker still, is that intelligence is common but inherently self-limiting, that the same cognitive abilities that allow a species to develop technology also lead it to prioritize short-term gains over long-term survival, to exploit resources faster than they can regenerate, to compete rather than cooperate, to destroy rather than build. If this is a universal feature of intelligence, a flaw baked into the structure of minds that arise through natural selection, then the peak might have produced billions of civilizations, and every single one of them might have failed for the same reason. This solution suggests that the silence is not an anomaly but a law, that intelligence is self-defeating, that the universe selects against minds, and we are simply the latest iteration in a long history of failed experiments. It suggests that the peak was not the golden age, but the killing fields, a time when life arose in abundance and died in equal measure, unable to overcome its own nature. But there is another possibility, one that inverts the entire question. Perhaps the silence is not a failure of intelligence, but a choice. Perhaps advanced civilizations are common, but they have learned to be quiet, to avoid broadcasting their presence, because the universe is dangerous and advertising your location is a risk no one takes. Perhaps the peak was the era when young, naive civilizations sent out signals. And perhaps they learned, through hard experience, that silence is survival. This solution is called the dark forest hypothesis, and it paints the universe as a place of existential competition, where every civilization is a potential threat and the only safe strategy is to remain hidden. If this is true, then the decline is not a winding down but a going underground, a transition from a noisy, visible universe to a quiet, invisible one, where civilizations exist but do not reveal themselves, where intelligence is common but communication is rare. The peak, in this framework, was the last time the universe was loud. Now it is silent, not because it is empty, but because everyone is hiding. None of these solutions can be proven with the data we have. The Fermi paradox remains open, unresolved, a question that sits at the intersection of cosmology, biology, and philosophy. But the peak adds urgency to the question. If we are living in the decline, if the opportunities for life are decreasing, if the universe is winding down, then the window for intelligence to arise and spread is closing. Every billion years that pass, the universe becomes a little less hospitable, a little less capable of supporting the complex chemistry that life requires. If we are alone, then we are the last chance, the final spark before the darkness. If we are not alone, then the others are also facing the same constraints, the same decline, the same narrowing window. This changes the stakes. It means that the search for other intelligences is not just a scientific curiosity, but an existential question. A search for evidence that minds can survive, that the great filter can be passed, that the decline is not the end of intelligence, but a challenge to be met. It also means that if we fail, if we do not survive, then we have squandered something irreplaceable. Not just our own potential, but the potential of the cosmos itself. The brief moment when the universe is capable of producing minds, and those minds are capable of understanding it. The silence of the universe is not neutral. It is a warning. It tells us that intelligence is not guaranteed, that survival is not automatic, that the curve we are living on slopes downward, and we are riding it toward an ending we cannot yet see. But warnings can be heeded. The curve can be understood. The decline can be measured, studied, perhaps even slowed. Not the cosmic decline, which is beyond our control, but our own decline, the processes that threaten to end us before we have had a chance to see what we might become. The universe peaked 8 billion years ago. But humanity has not peaked. We are still rising, still learning, still building the tools and the knowledge that might allow us to survive the decline, to outlast the stars, to find a way to persist even as the cosmos cools around us. This is the task. Not to reverse the decline, which is impossible, but to navigate it, to find a path through the dimming universe that allows complexity to continue, that allows minds to endure, that allows the question of existence to be asked and answered for as long as the laws of physics permit. The peak is behind us, the silence is ahead, but we are here, now in the space between, and what we do in this space matters. There is a specific image that cosmologists use to visualize the history of star formation. A graph with time on the horizontal axis and star formation rate on the vertical axis, and the curve that rises and falls across it. The curve is not smooth. It is jagged, full of small fluctuations and uncertainties, but the overall shape is unmistakable. A rise in the first few billion years, a peak around 5 to 6 billion years after the Big Bang, and then a long, slow decline that continues to the present and extends into the future, asymptotically approaching zero but never quite reaching it. This curve is reproduced in hundreds of papers, refined with each new data set, debated in conferences and seminars. It is one of the foundational results of modern cosmology, a piece of the puzzle that fits together with measurements of the expansion rate, the cosmic microwave background, the distribution of galaxies, the abundance of elements. It is a curve built from light, from photons that have traveled across billions of years to reach our telescopes, carrying information about the stars that emitted them, the galaxies that hosted them, the era of the universe they came from. But the curve is also an abstraction. It flattens the complexity of the universe into a single line, averages over billions of galaxies, erases the individual histories of stars and planets, and the countless processes that turned hydrogen into helium, and helium into carbon, and carbon into life. It is a summary, a reduction, a way of making the incomprehensible comprehensible, of turning the vast and chaotic history of the cosmos into something that can be drawn on a page and understood at a glance. And yet, for all its abstraction, the curve is real. It describes something that happened, something that is happening, something that will continue to happen. It is not a metaphor. It is a measurement, a record, a testament to the universe's own history. When you look at the curve, you are looking at time made visible, at the entire lifespan of the cosmos compressed into a shape you can hold in your mind. You are seeing the rise and fall of creation itself, the arc of the universe from silence to light to silence again. You are seeing your own position in that arc, the moment when you exist, the narrow window when the stars are still shining, but the peak is already past. This is what cosmology offers, not comfort, but clarity. Not meaning, but precision. The curve does not tell you why the universe exists or what your purpose is. It tells you when you exist, where you are in the story, what has come before, and what is coming next. It gives you a map, a timeline, a context. And context changes everything. Knowing that the universe peaked 8 billion years ago does not make the stars less beautiful. It makes them more precious. Knowing that the decline is real does not make existence meaningless. It makes it finite, specific, irreplaceable. You are here, now, in the aftermath of the peak, in the long twilight of the cosmos. The stars are dimming, the gas is dispersing, the galaxies are separating. But you are still here, still capable of seeing the stars, still capable of asking why they shine and how long they will last, and what it means to live in a universe that is winding down. This is not a small thing. It is everything. The future of the universe, extrapolated from the curve, is a landscape of cold and darkness, punctuated by the occasional flicker of a red dwarf or the slow evaporation of a black hole. Star formation will continue for roughly another trillion years, but at an ever-decreasing rate, producing mostly low-mass red dwarfs that burn slowly and faintly for tens or hundreds of billions of years. The last stars will form perhaps 1 or 2 trillion years from now, in isolated pockets where enough cold gas has managed to accumulate despite the expansion and heating of the universe. After that, no new stars will form. The universe will be filled with the remnants of dead stars, white dwarfs, neutron stars, black holes, planets, asteroids, dust. These remnants will persist for an incomprehensibly long time. White dwarfs will cool into black dwarfs, inert spheres of carbon and oxygen that emit no light. Neutron stars will cool as well, radiating away their residual heat over trillions of years. Planets will drift through the darkness, frozen and lifeless, their surfaces untouched by sunlight for longer than the current age of the universe. Black holes will be the last objects to disappear, evaporating through Hawking radiation, a process so slow that a black hole with the mass of the Sun would take 10 to the 67th years to evaporate completely, and a supermassive black hole would take 10 to the 100th years or more. These numbers are absurd. They are larger than anything the human mind can comprehend. They make the current age of the universe, 13.8 billion years, look like the blink of an eye. They suggest a future so long and so empty that calling it a future seems misleading. It is more like an eternal present, a static state where nothing changes because there is no energy left to drive change, no gradients left to exploit, no differences left to generate motion or thought or life. This is the heat death of the universe, the final state predicted by thermodynamics, the point at which entropy reaches its maximum and the universe settles into equilibrium. It is not a dramatic ending, not a big crunch or a big rip, but a slow fade, a gradual exhaustion, a dying of the light. But even this far future is not entirely featureless. There are still processes, still events, still things happening, just on timescales so vast that they defy imagination. Protons, the building blocks of atoms, might decay, a process that has never been observed but is predicted by some theories of particle physics. If protons decay, then all the matter in the universe will eventually dissolve into radiation, into photons and neutrinos and other particles that will continue to expand and cool until they are spread so thin that they might as well not exist. Or perhaps protons are stable, in which case matter will persist forever, but it will be locked into forms that cannot do anything interesting. Stars will be gone. Fusion will have stopped. The only energy available will be the slow decay of black holes, and even that will eventually run out. Or perhaps the universe will surprise us. Perhaps there are processes we have not yet discovered, laws of physics that only become relevant at timescales of 10 to the 100th years or longer. Mechanisms that can generate structure even in the far future, even in a universe that appears dead by our current understanding. This is speculation, but it is not idle speculation. It is the natural extension of the question raised by the peak. If the universe has a history, if it has a curve, if it has a shape in time, then what is the final shape? What is the endpoint? What happens when the curve reaches zero and stays there? We do not know. We cannot know, because the timescales involved are so far beyond anything we can observe that they exist only in the mathematics, in the equations that describe the behavior of matter and energy and space. But the equations are consistent. They point to a future that is cold, dark, and nearly empty. A universe that has exhausted its potential and settled into a state from which nothing new can emerge. This is the long-term trajectory of the decline. Not just a dimming, but a dissipation, a dissolution, an ending that is not sudden but inevitable. And yet, within that trajectory, there is still time. An incomprehensible amount of time. 1 trillion years is 1,000 times the current age of the universe. It is long enough for entire cycles of stellar evolution, for galaxies to merge and separate, for civilizations to rise and fall 1,000,000 times over if they can find a way to survive. The decline is real, but the decline is also slow, and slowness creates space, creates possibility, creates a window within which things can still happen. This is the paradox of the decline. It is both a closing and an opening, both a limit and an opportunity. The universe is winding down, but it is winding down so slowly that there is still room for everything we can imagine and more. The question is not whether the decline can be stopped. It cannot. The question is what can be done within the decline. What kinds of structure can be built? What kinds of complexity can be sustained? What kinds of minds can endure in a universe that is growing colder and darker with every passing billion years? This is the challenge facing any civilization that hopes to outlast the stars, not to reverse the curve, but to adapt to it. To find ways to extract energy from sources other than fusion, to build habitats that do not depend on sunlight, to preserve information and continuity across timescales that dwarf the lifespan of any star. Some physicists have speculated about the possibility of civilizations that harvest energy from black holes, using the Penrose process or Hawking radiation to extract usable work from the gravitational field. Others have imagined civilizations that slow their metabolism, that think and act on timescales of millions or billions of years, stretching their existence across the entire decline by moving in slow motion, using energy so sparingly that they can persist long after the last stars have died. These ideas are speculative, but they are grounded in physics. They are not fantasies. They are extensions of what we know about energy, entropy, and the conservation laws that govern the universe. They suggest that the decline is not the end of possibility, but a transformation of possibility, a shift from fast, bright, energetic processes to slow, dim, efficient ones. If intelligence can make that shift, if minds can adapt to the decline, then the curve of star formation is not the curve of intelligence. Intelligence can outlast the stars, can persist in the darkness, can find ways to exist that do not depend on the processes that created it. But this requires foresight, planning, and a willingness to think on timescales that are alien to the human experience. It requires letting go of the idea that the future should resemble the past, that the golden age is something to return to rather than something to move beyond. It requires accepting the decline as a condition, not a catastrophe, and asking what can be built within that condition. This is not a narrative humanity is comfortable with. We are creatures of growth, of expansion, of progress. We measure success by accumulation, by brightness, by the upward slope of the curve. The idea of a universe in decline, of a future that is dimmer and quieter than the past, runs counter to every instinct we have. But the universe does not care about our instincts. It follows its own laws, its own trajectory, and that trajectory is clear. The peak is behind us. The decline is real. The future is darker. And yet we are still here, still asking questions, still building telescopes and writing equations and trying to understand the curve we are living on, still capable of wonder, of awe, of the recognition that even a declining universe is a universe, that even a dimming cosmos is a cosmos, that even the long twilight is full of light if you know how to look for it. The stars are fading, but they have not faded yet. The gas is dispersing, but it has not dispersed entirely. The universe is winding down, but it is still wound, still full of motion and energy and potential. The curve is falling, but it has not reached zero. This is the moment. This is the window. This is the time when the universe can still be known. when the evidence of its history is still accessible, when the stars are still bright enough to see and the minds are still sharp enough to understand. We are living in the aftermath of the peak, but the aftermath is not the end. It is the middle, the long middle, the era when the universe is old enough to be interesting and young enough to be observable. It is the era when complexity is possible, when life can emerge, when intelligence can ask questions and find answers. This is the gift of the decline. Not brightness, but time. Not energy, but structure. Not the frenzied creativity of the peak, but the patient, deliberate construction of systems that can endure. The universe peaked 8 billion years ago, and we are living in the collapse. But the collapse is not a failure. It is a process, a transformation, a slow unwinding that creates the conditions for everything we are and everything we might become. The fire is going out, but the embers are still warm. And in the glow of those embers, we are here, watching, learning, asking what it means to exist in a universe that is fading but not yet dark, winding down but not yet still. The peak is behind us. The silence is ahead. And we are in between, living in the narrow window when the universe is both knowable and finite, both magnificent and mortal. This is not a time of despair. It is a time of clarity. The curve is drawn. The trajectory is clear. The question is no longer what will happen, but what we will do with the time we have. The light we can still see. The structure we can still build. The universe is collapsing, but collapse is not the same as extinction. It is a change of state, a movement from one form to another, a story that continues even as the conditions shift. And we are part of that story. Not the beginning, not the end, but a chapter in the middle, written in the aftermath of the peak, in the long decline, in the dimming light of stars that were born when the universe was brighter and will die when the universe is darker. We are here. Now, in the collapse. And the collapse is where we live.